Thank you very much for the introduction. I would like to thank the jury for being present here today. And thanks to all of you for attending this presentation, which is entitled Image Processing for Art Investigation, and which is supposed to give you a non-technical overview of the work I've done in the context of my PhD. But before I do that, I would like to show you an image. This, as most of you will know, this is an image of the Ghent altarpiece. It was painted by the brothers Van Eyck. It was finished in 1432. And this image was taken into the context of a large-scale acquisition project that had the goal to assess the state of preservation of the altarpiece and to decide whether it needed to be restored or not. And what they did, they acquired it with different techniques and in very high resolution. So this is how it looks like when it's opened. And this is how it looks like when it's closed. And just to give you an idea of the resolutions we're able to attain with modern photography, let's zoom in on one of the panels. This is the panel of Elisabeth Bourlu during the restoration. And let's zoom in on her hands a bit further. And this is about the maximal resolution that we're able to attain nowadays. So as you can imagine, this is a wonderful tool for art experts to use, but it also comes with a number of challenges. For example, for storage, but also in analysis of these huge amounts of data. And this is exactly where my PhD comes into the play. It has the goal to develop a set of non-invasive digital image processing tools in the aid of art scholarship. Non-invasive, it means that we do not have to touch or harm the painting in any way to be able to analyze it. And so we apply these algorithms on high resolution and multimodal images in order to help in find solutions in, for example, in conservation, in the further prevention of the degradation of the painting, and many others. So what are the tools that we have at our disposal? Well, first of all, we have what I showed you before already, visual macrophotography. And on the right, you can see photographer Luc van Meulen during the acquisition of the Ghent altarpiece. On the left, you can see a Van Gogh painting with a nicely zoomed-in brushstroke. A very common way of acquiring paintings in visual macrophotography is to put one of the light sources on the side of the painting so that the light illuminated by this light source literally rakes over the surface of the painting and nicely emphasizes the structure of the surface. For example, here you can see the canvas or some brushstrokes or some cracks appearing. They do the same during the restoration of the altarpiece, and here you can see that the cracks are nicely emphasized. Next to visual macrophotography, we also have infrared photography and reflectography. And there, some paints become transparent under infrared light. And they are mostly used to uncover underdrawings, so the initial sketches of the artist when he's making the painting. And for example, you can see that with infrared reflectography, there's even a bit more that becomes transparent. These greens are black in the photography, but they become transparent in the reflectography. Another tool we can use is X-ray imaging. And on the left, you can see here an acquisition setup and the very first X-ray ever taken by William Röntgen of the hand of his wife. And unlike most of what my colleagues think, this is not a tumor. This is her wedding ring. And this is how a painting looks like under, with an X-ray, and surfaces, very thick surfaces or materials that contain metals will appear bright on images like this, while holes and cracks, well, they appear very nicely delineated and dark. And here you can even see the canvas becoming very prominent. So it's a very nice tool in preservation sciences, conservation sciences. We were also very, very lucky to be able to work with multispectral imaging. Normal color photographs, they consist of three components: red, green, and blue color. Now, with a multispectral image, we have many more. In this case, we have 13. We have 13 measurements taken at discrete points in the electromagnetic spectrum. 9 of them reside in the visible domain, 1 is in the UV, and 3 lie in the infrared. So basically what we do is we extend our view on the painting beyond what is visible with the naked eye. And this is the acquisition here at the Royal Museum of Fine Arts, where this is the camera. And here you can see 2 light sources that are placed on the side of the painting. And these light sources rake over the surface of the painting 13 times. What can we do with these multispectral images? Well, we can choose to take the acquisitions at specific wavelengths corresponding to the color red, green, and blue, and make a color reconstruction of the painting. Now, we could choose to also mix it up a bit and take the acquisition at the infrared wavelength, put it in the red channel, the red put it in the green, and the green put it in the blue. This gives us a very different representation of the painting as we did before. And let me show you this in detail. So this is just the photograph of that painting, and this is the false color representation. And so you can see that there are a lot of things happening here. These are actual restorations that were made at a later stage and are not visible with the naked eye. Now, since we have so much data at our disposal, we can imagine a whole range of processing. And this, for example, is a processed image that has been done on this part of the painting. And you can we were able to determine or discover two types of restoration. On the one hand, we have the application of mastic, which is a substance that is used to cover cracks, to fill in cracks. And here are actually the application of very tiny brush strokes that are applied to hide cracks and are not visible with the naked eye. These are actually the results of the very first baby steps I took during my PhD, and the initial results, or the results of this research, can be seen now in an exhibition that is going on at the Royal Museum of Fine Arts. And for those that would be interested in visiting it, this is the link. So just go on their website and click on exhibitions. Now, for the core of my presentation, this actually consists of three parts. The first part is an image enhancement part. The second part is about the automatic detection of cracks within paintings. And the last part consists of a set of tools that can be broadly brought under the main topic of art forensics. So the first thing we did in image enhancement was the removal of canvas in high-resolution images of paintings. So these are the partners of that project. On the left, you can see Professor Frederik Leen of the Royal Museum of Fine Arts of Brussels. He's the head of the Department of Modern Sciences at the museum. And Etienne Van Vive, who I saw is present here today, which is very nice. He's a restorer and works a lot with people from the museum. And so the painting we studied most is called The Portrait of Susan Bambridge. It was painted by Paul Gauguin during his trip in Tahiti in 1891. And as you can see from this detail, the canvas, it was painted on a very rough type of canvas, and the canvas becomes very prominent in these type of images. And at one point, Etienne asked us if it was possible to remove this effect, to remove the canvas from the painting, from the image of the painting. But before I explain you how we did this, I should explain you what an image consists of. So if you zoom in really far into the image, you can see that an image is nothing more than a collection of colored dots or pixels. And each of these pixels is a combination of the colors red, green, and blue. Now, this is one possible representation for a pixel, but you could also choose to have a luminance, chrominance representation, where the luminance is nothing more than the intensity of the pixel, while the chrominance says something about the color of the pixel. So the idea was to develop an image filter that was able to remove these canvas artifacts from the photographs of a painting. So how does imaging filtering work? Well, like I said, an image is nothing more than a grid or a matrix of numbers, and where each element in the source image is called a source pixel. A filter is also a matrix of numbers, where each element now is called a filter coefficient. And our filtered image, every pixel is called a target pixel. So how does this filter work? Well, it acts on the same size as its own size in the source image, and it determines the value of this target pixel in our filter image as follows. So you can see, for ease of explanation, I chose only two non-zero coefficients here in the filter. And these are actually multiplied with the corresponding source pixel in our source image, and then added up, which gives us the value of our filtered pixel. And this is done, so this filter is slid over the entire image, and so we will fill in every target pixel in our filtered image. By choosing these values for these filter coefficients in a smart way, we can actually imagine a whole range of processing. We could, for example, blur our image. We could decide to sharpen the details within our image, or we can even imagine making a filter that emphasizes edges within the image. In this case, this is a filter that emphasizes horizontal edges within the painting. So let me go a bit into detail to show you this. So this is the original, the blurred version, an enhanced version, and this is a detection of the horizontal edges within the image. So the idea was to create a filter that is able to remove these canvas artifacts from the painting. But first we need a nice model for our image, and we took this model from the world of denoising, where we have a received signal, which is supposed to be the superposition of an original very clean signal and an independent noise component. We decided to change terminology somewhat, and we don't talk about denoising anymore, but we talk about decanvassing, where our contaminated painting is a superposition of a canvas-free component or a decanvassed painting and an independent canvas contamination. So the filter we decided to create is called the Wiener smoothing filter, and when you apply it to this contaminated painting, it gives us an as close as possible representation of the image without canvas. And how is this filter constructed? But usually it's constructed by using autocorrelations. And autocorrelations can be seen as something that describes the similarity of the image, but at different spatial offsets. So it's a mathematical tool to detect periodic structure within a painting, within a signal. So how do we determine these autocorrelations of, on one hand, our canvas-free painting, and on the other hand, that one of our canvas contamination? Well, we decided to extract a patch of the painting, so a little part of the painting that doesn't contain canvas, one that does contain canvas, and we calculated the autocorrelations for both of them. Now you can see that the autocorrelation on the right contains a very strong periodic component that is not present in the autocorrelation on the left. This can only be the attribution of the canvas itself. So we decided to model the autocorrelation for a canvas-free painting. We did the same for our noise component, our canvas component, and when we superimpose these two, you can see that you approximate the real autocorrelation very well. So we're able to construct this filter. So, and when we apply it on a piece of the painting, this is a result. So let me jump back and forth a number of times so that you can really see the difference between those two. And when we subtract one from the other, this is what we removed from the image. I did the same thing on the larger portion of the painting, and this is the filtered version. So I would, maybe the clearer part is around here. So let me go back and forth a number of times, and you can really see the difference. So now what happens when, this is all very well when the canvas behaves very nicely in a grid-like fashion. But what happens when we have other weave patterns? So for example, here, this is a very different weave pattern of what we had before. Well, then we decide we introduce another image processing technique, which is called source separation. And source separation considers the following model. So we have two sources. On the one hand, our painter. On the other, our canvas. When the painting is made, we have something that's called a mixture signal, and we apply a source separation algorithm, which will give us an as close as possible representation of each of these two sources. So on one hand, we have our painting, on the other hand, we have our canvas. The source separation technique we applied is called MCA and stands for Morphological Component Analysis. And MCA is based on the idea of choosing your dictionaries very well. And what is an image dictionary? So I said before that an image is nothing more than a collection of pixels, a collection of numbers, basically. Well, you can also construct an image by linearly combining building blocks. These building blocks are called atoms, and here you can see some example of these atoms here as well. And a collection of these atoms is called an imaging library or an image library. We have the choice. We can choose a fixed generic dictionary, and I think the most famous here is the discrete cosine dictionary, the DCT dictionary, which is also used in JPEG representations of an image. Or we can learn to adapt our image to learn our atoms from the image itself. And here you can see that these dictionary elements, they nicely follow the structures within our image. So MCA is based on the idea that there exist two of these dictionaries that optimally represent each of our two components. So let's, yes, and we need a very good description of our components in order to choose our dictionary. And on the one hand, we have canvas, which can be described as being roughly periodic, which motivates the choice of periodic atoms, and these come from the global discrete cosine transform. And painting is what we call in image processing a piecewise smooth image signal. And there from literature we know that a dual tree-complex wavelet transform is the optimal choice. So let's apply both methods to a painting that contains some canvas. I hope it's clear here. So, and here you see our result by applying the filter, where this is a difference with our original. This is actually what we removed from the painting. And this is the result when we apply MCA. And in this case, it could be said that, for example, MCA removes a bit too much. It seems to remove the very tiny brush strokes that you can still see here, and that the Wiener filter still remains, under Wiener filtering, it stays intact. So let's do it on an other image. And here, on the other hand, you can see that the filtering actually leaves a bit of the canvas still in the image, while the MCA nicely removed the entire canvas from the original. And at this point, I should thank Charlotte Kaspers, who is the painter that made these paintings. She's a very gifted painter. She worked on a lot of scientific projects involving art, and she's specialized in art reconstructions. So here you can see a reconstruction of a part of the Ghent altarpiece, and here is one of her reconstructions from a Van Gogh painting. Let's move on to the next topic, which consists of the removal of cradling within high-resolution X-rays of paintings. So far I talked about canvas paintings. Now we'll move to the topic of paintings that were made on wood. And a very common restoration technique is to attach wooden bars to the back of these panels, in order to reinforce them. And this is a schematic of how this works. And this is just a picture taken from the back of one of these paintings. This is joint work together with Rachel Lynn at the Duke University, who kindly made this schematic. So, and when we look at an X-ray of a painting like this, you can see that we have this grid, and this is very annoying for art expert while studying the painting, so we were asked to remove them digitally. So again, we see this cradle removal as a source separation problem, but now our sources are very different. On the one hand, we have a cradling component, and on the other hand, we have the panel painting itself. So we wish to separate those two from our original. And so the schematic goes as follows, the model goes as follows. We have our original image I. It can be subdivided in a panel component, into a cradling component, and each of these contains what we call a cartoon part. And the cartoon part in the panel painting is nothing more than the image, the depiction of the painting itself. And here in the cradling, it is this constant intensity shift that appears on the X-rays because of the thickness of the cradling. And they each have a textural part which consists of the wooden texture that made up these two components. So we propose a three-stage approach in order to remove them, to remove this cradling. So we have our original image. In a first stage, we remove this constant intensity shift caused by the cradling. In a second stage, we apply what MCA again, this source separation technique again. But the problem there is that MCA is not able to make a distinction between the texture from the panel and that from the cradling. So it removes everything. And this is this texture component you see here. So in the third stage, we need to train a model that makes a distinction between these two types of textures. And here you can see that we nicely extracted the texture part of the cradling, which after we remove it gives us this, the panel painting component, which is exactly what we wanted to retrieve. And here you can see our two sources that are separate, the cradling and the panel painting. And this removal of cradling is at the museum is done manually and is done by using Photoshop, and it's a very tedious job. And our method is faster, and you can see that we have slightly better results because we're able to remove this texture that here is still present within the image. This is an example where you have a part of a Rubens painting that was acquired by X-rays, and here you see that the cradling is still attached. And here, this is an X-ray when they physically removed the cradling, and then they took the X-ray again. And this is after our decradling algorithm. So let's move over to the second big topic of the talk, which is about the automated detection of cracks. And there we have two scenarios. The first one is detection of cracks within a single modality. And this data set consisted of very high resolution scans of photographic negatives taken from the Ghent altarpiece, which was the only data that was available at that time. And in a second scenario, we will talk about the newly acquired data set, so multiple modality data set, and I will talk about that later. So the single modality, this is an example, this is a detail, where you can see that these cracks can behave like dark elongated structures on a bright background, or the other way around, they are bright elongated structures on a dark background. And this is the workflow of the detection method. So first we have some pre-processing, which basically consists of removing noise from these images. Then we propose 3 distinct crack detection methods, which we will, the results of which we will combine by using a voting scheme. So the first method is based on creating a set of oriented and elongated filters. Our original image is filtered with each of these filters, which emphasize elongated structures within the image. Then we will threshold these images, meaning that we go to a